Okay, so today we will cover Chapter 5 and a little bit of Chapter 6. And then next week we'll finish Chapter 6, and then the week after that is the midterm exam, right? So next week we have a quiz, and then the week after we'll have the midterm exam. Okay.
Next week is a quiz.
Yes.
Is that cumulative?
No.
Thanks.
Yeah. The midterm is cumulative, of course. All right. So let's cover chapters 5 and 6. Okay. So chapter 5 is on sampling distributions, and chapter 6 will be our introduction to inference, which will be confidence intervals. We're already halfway through October, and then it will be November, and then December. I guess that's how time goes, but it just goes by quickly. Okay. All right. So we are. Let me see if I can pull up that slide that I bring up every so now and then. Which kind of maps out no, this is not it. Am I going crazy? I have to sort by date, and that's what's going on. Oh, okay. So, so last week we covered random variables and probability distributions. And so today, building off of our understanding of the normal distribution specifically, we're going to learn about the central limit theorem, okay? And sampling distributions, which the central limit theorem applies to. And then today we will get to just introduce this topic of inferential statistics, okay? So, here we're still, the first part of this class takes our understanding of probability and the normal distribution, and then we're going to, at the end of the class, apply it to making inferences about the population. Okay, so I think on the very first day of class I said, one of the big reasons why we study statistics is so that we can make conclusions about the population based on limited data. So even though we just have a sample, we can generalize, like we can observe this sample and make conclusions about the entire population, even though we've only seen this small little piece. All right, so let's talk about sampling distributions and what a sampling distribution is in the first place. Okay. So we start off with some population. Okay. And from that population, I'm going to take a little piece, assuming this population is all shuffled up. I'm going to take a little piece out of it, and this will be my sample. Okay. Now, if I look at the sample itself will have a distribution, okay? But that's not a sampling distribution, right? So the population has some distribution, and the sample, let's say I had 30, I selected 30 random people to be part of my sample. If I look at the distribution of those 30 numbers, that would be the distribution of that sample, okay? So let's say there are n equals 30 people. In the sample. And just like any data set, I could build a histogram out of these 30 observations. Okay. And this distribution is the distribution of the sample. Okay. Or confusingly, we could call it the samples distribution, okay? But that is not the sampling distribution. So this is the samples distribution, but this is not the sampling distribution where I have a ing over there. Okay. So what is a sampling distribution? Well, from this sample, I could boil the entire sample down to a single number. Okay. We can use a summary statistic, and I can calculate the mean of the sample. What is the symbol that I use for the mean of the sample? Y bar, okay? Other textbooks might say X bar, but it's the same thing, okay? The mean of the sample, Y bar. So I boiled our sample down to a single number. Let's say I go back to the population, okay? So we go back to the population, I take another random sample, okay? So this is a and I do, and this sample also has n equals 30, so same n. And what we're doing is we're going to also boil this down to a single number. So we get another y bar. How will this y bar compare to this y bar? Will they be the same? Not necessarily, right? We expect them to be, somewhat in the vicinity of each other, right? If I take 30 random people and I calculate the average weight, and I take another group of 30 random people and I calculate the average weight, we expect them to be in the same ballpark, okay? But we're not going to expect them to be exactly the same. Okay? So far, so good? Okay, and so the sampling distribution is, I'm going to repeatedly take thousands and thousands of these, okay, of these samples. Every single time, I'm going to have the same size n, same n, and we calculate y bar, okay? We're going to keep track of every single y bar. And the sampling distribution is the distribution of all the different y bars I observe. I should say this is the sampling, this technically is the sampling distribution of the sample mean. So it's the distribution of all the different y bars that I observe. So I just want to make sure conceptually this is okay. So I'm repeatedly going to the population, taking a random sample from the population, looking at that sample. For each sample, I'm going to calculate a y bar, and then we keep track of this, okay? And I do this over and over and over and over again, okay? So the true sampling distribution is actually every single possible y bar from every single possible sample that could be drawn from the population. And so, you know, if you have 1 million people in the population, every single possible sample would be 1 million choose 30, which is an astronomically huge number. But the sampling distribution would technically cover every single possible one of those. Usually it'd be very difficult to calculate the exact sampling distribution, so we can simulate it using, you know, like 10,000 random samples or 100,000 random samples from a population. But that would be the sampling distribution, okay? And I should be specific and call it the sampling distribution of the sample mean, because we could pick another sample statistic like the standard deviation and follow this process of repeatedly taking samples and every time boiling the sample down to a single number. And in that case it would be the standard deviation. And we would look at the distribution of all the different standard deviations we observe. Or whatever other statistic you want. You could have a sampling distribution for any statistic. In our class, we're only going to focus on the sampling distribution of the sample mean, okay? So when I talk about sampling distributions in this class, it's about the sample mean. But I don't know, should you encounter more statistics in the future, I would say, you know, 90% of the time if they talk about a sampling distribution, it's going to be about the sample mean, but there might be other situations where you're dealing with a sampling distribution of some other statistic, and then the properties we learn about sampling distributions do not apply to the other sampling distributions, okay? So when I talk about stuff, I'm only talking about sampling distributions of the sample mean here. But we're gonna learn about stuff and the central limit theorem and all of that. It's very good. Okay, so the question is, what does this sampling distribution look like? Okay. Okay, so I will write of the sample mean here one last time, and it will just be assumed for the rest of the class when I talk about the sampling distribution, I'm talking about the sampling distribution of the sample mean. Is that okay? So I don't have to keep writing of the sample mean every single time. Okay, so what does the sampling distribution look like? Well, let's find out. Okay, so I'm going to run some simulations here in R to illustrate kind of what a sampling distribution could look like. Okay, so what I'm going to do is I'm going to create a population. All right. Now our population could be anything. It could be just any population of values. So we could go around and we could ask people, you know, what is, we could have, you know, 10,000 people. Let me just, I'm going to round to 0 here. Oops. All right, you don't have to copy all of this code down. But here, what I'm doing is I'm creating a population okay, and so this is my population. This is I have a normal distribution for the population, and this is approximately something like IQ scores, something around with a mean of around 100 and a standard deviation of about 16. We could actually, here, because I have the entire population, we can actually find out the mean of the population, which is 99.9903, and the standard deviation of our population, the exact value is 15.93. Okay, and so I'm going to simulate taking a random sample of 30 people, okay, from our population. So I'm going to say we're going to sample from the population. I'm going to draw 30 people, and if I do that, this represents 30 randomly selected people and their IQ scores. So here, our first person has an IQ of 102. The next person we randomly selected has an IQ of 99, so on and so forth. This person has an IQ of 116. This person has an IQ of 66, so on. I've got a total of 30 people here, okay? And every time I run this command sample, it goes into the population and it draws 30 new people, okay? So every time I run this, it does this, okay? So I can store this as just kind of, we'll call it X, and then I can then ask what is the mean of X, okay? So here, these are the 30 people I've randomly selected, and if I take the mean of those 30 people, I get a mean of 98.7. Okay, so if I add up these 30 numbers and divide by 30, I would get 98.7. Is that okay? All right, and so what I can do then is I can have R run this thousands of times, okay? I can create a loop, and every time I run the loop, it's going to perform this operation. It's going to take a sample, and then it's going to find the mean of the sample. And then what we're going to do is we're going to store every single mean that I observe. Okay? And so to do this, I'm going to create something called sample means. And what sample means will start off being a bunch of NAs. I'll do this 10,000 times. Okay? 10 to the 5th is, no, 10 to the 5th is 100,000, so 10 to the 4th. Okay, so I'm going to just create a loop, and don't worry about the exact code that I'm running here. So here I am running a loop, and it says for I in 1 through 10,000, okay? That means look at these numbers 1 through 10,000, and for every single number you see, do this, okay? And what you're going to do is you're going to take a sample from the population of 30 people and store it into X, and then you're going to find the mean of X, and the result of that you're going to store in sample means. But where are you going to store it? You're going to store it in position I. Okay, so the very first time it runs, it's going to store it in position 1, and then when it runs it again, now I has changed to the value 2, and it's going to store the mean of the sample in position 2. And then the third time, it's going to store it in position 3. So on and so forth until it gets to 10,000, and it stores the mean of the sample in position 10,000. Does this make sense? Yes.
What do you mean by position? Like people or?
So R handles values in what's called vectors, okay? And so when asked R to take a sample of 30 numbers, okay, and I store it into X, and I say, you know, what is X? And it tells me these are the 30 numbers. X actually has 30 positions in it. The very first position is 78. The second position has 110. The 23rd position, as indicated by these brackets, is 79. And the very last one, the 30th position, would be 75. Okay, so we're gonna run this. And we go boom. Okay, and it's done. It did this 10,000 times. It's done. And so we can then look at what the sample means themselves look like. Okay? So I'm going to create a histogram of the sample means. So what do you think the histogram of the sample means will look like? So this is the distribution, the sampling distribution here. This is what do you think it's going to look? How do you think it's going to look? Okay, normal. What do you think the mean of the sample means will be? So we're drawing from a population where the mean is 100 and the standard deviation is 16. Okay, and now I'm taking samples of size 30. So what do you think the mean of these sample means are? Around 100, okay? So that makes sense. What do you think is going to happen to the standard deviation of the sample means? Bigger, smaller? Okay, let's take a look. Okay, so remember, this is the histogram of our population, okay? So, you know, we have a standard deviation of about 16, which means, you know, almost everybody's between, you know, around, you know, 70 and 130. Okay. Okay, let's make this histogram. Okay, let's take a look. Okay, so it still looks normal, but what do we notice about the spread? Well, if we look at the scale, so I apologize, the scale, we notice that, so previously our last plot has, so this is the population, you know, it looks like almost everybody, just a few outliers beyond, almost everyone's between 60 and 140, okay? And if I look over at the histogram of sample means, what do we notice? Almost everybody is now between like 92, 93, and 108. Do we see that? So what happened to the spread? It shrunk. Okay, so let's think about that. Why is the spread shrinking here? So when we looked at the population, okay, are there people who have an IQ of 60? Yes, but are there very many of them? No, there's not, okay? But, you know, what's the probability of drawing someone with an IQ of 60? We could figure that out, right? We would do the normal distribution, 60 minus 100 divided by 16, find the z-score and look it up, okay? Let's think about a sample of 30 people now. If I have a sample of 30 people, randomly selected people, what's the probability that the average of all 30 people will be an IQ of 60?
Really low.
That's now going to be really low, right? It would be for you to pick 30 random people, and then for the average of those 30 people to have an IQ of 60 would be incredibly rare, okay? It would almost never happen, okay? And that's because, you know, for it to have an average of 60, then that means all 30 people that you randomly select have to, you know, be on the lower end of the IQ spectrum, right? And if you have one person that has a high IQ, it has to be counterbalanced kind of by multiple people with very low IQs type of thing, okay? So I think that sheds some light as to why the histogram of sample means has a much tighter spread, okay? In that when you're taking samples of 30 people, it would be very unusual for all 30 people to have an average, really high or an average really low. And when you average all 30 people out, it's much more likely that the average of those 30 numbers is going to be somewhere close to the middle, seemingly between 95 and 105, okay? Whereas, it was not unusual to pick a random individual and that person to have an IQ of 110, okay? So 110 is like right here, so it's like very likely to pick a random individual to have an IQ of 110. But then to take 30 random people, so again, the key is that we're randomly selecting people. If we randomly select 30 people, it becomes very unlikely for the average to be 110. And so we see the spread shrinking here. Okay. And so we can calculate these things. So we have all the sample means we observed. So we can get the mean of the sample means. And so that's very close to the population mean, which is like almost 100 exactly. And the standard deviation of the sample means we can see is only around 2.92. Okay, whereas the population standard deviation was around 16. Here the standard deviation of the sampling distribution of all the sample means we've observed is less than 3. Are there any questions? Okay. What would happen if I changed my population? Okay, so my population, so here my population is normally distributed. Okay. What if my population is uniform? So what if I say my population is going to be the digits 0 through 99. Okay. So this is just a funny artifact of the default settings for the histogram, but in that this one counts from 0 to 5, and this one only counts from 95 to 99. So this one only has 4 numbers in it, and this one has 6 numbers in it. So it's just a funny artifact, but don't worry about it. This just means all the numbers between 0 and 100, or at least from 00 to 100 are equally likely, or maybe I could even just do 1 through 100. That'll probably fix my problem here. Okay, so here I've created the digits 1 through 100, or numbers 1 through 100, and this is the population. Okay, so just imagine I passed out numbers 1 through 100, and I said, and now I'm going to take random samples of 30. Okay, and to help, I'm going to take samples with replacement. Okay, which means so if I pass out numbers 1 through 100 to 100 people, I'm going to say I'm going to take samples of 30. I'm going to draw a person, but I'm going to also put that person back in the crowd. So it's very possible to draw the same person again. Okay? So what do you think is going to happen here with our sampling distribution? So I'm going to, we can look at X. So these are the 30 random people that I selected. So our population has this uniform distribution. Everybody is equally likely to be selected. But I'm going to take random samples of 30 people, or 30 numbers between 1 and 100. And every time I do that, I'm going to take the average, the mean of those 30 numbers that I randomly select. What do you think our sampling distribution will look like? We have no idea. Okay, well let's see what happens. Okay, so if I take the mean of x, you know, we see the mean is like 57. Okay, I can run this again, and I take the mean again in here. The mean is 55. So let's do this. Okay, I'm going to just run a loop, 10,000 samples of size 30. It's done. Okay. All right, and let's graph this histogram of all the different sample means. Any inklings here?
15 is probably going to be the average.
Let's see. So this is our histogram of sample means. Okay. So the mean is probably 50.5 if I had to guess. Okay. And what does the shape look like? The shape looks normal. Okay. So let's investigate this a little bit. So let's take the mean of the 10,000 sample means that I calculated. Okay, it's 50.46, right? So if we look at the mean of the population, what's the mean of the population? 50.5, right? 1 through 100. I've got the numbers 1 through 100, so you know we could add them all up, Gauss's rule, then divide by 100, and we get 50.5. The standard deviation of our population is 29.011. If I ask for the standard deviation of my sample means, though, I get a standard deviation of 5.226. Okay, and looking at the shape is normal looking. So what's going on there? So again, if we think, you know, even though each number is equally likely to be selected, 0 or the number 1 is just as likely to be selected as the number 50, which is just as likely to be selected as the number 99, all of those numbers are equally likely to be selected. When I'm taking samples, let's say I just take samples of 10 people or 10 numbers, okay? For the mean of those 10 numbers or 30 numbers, however big your sample is, for the mean to be something like 99, what would have to happen? I would need all 30 numbers, or all 10 numbers would need to be like 100, 99, or 98. Okay? So it's incredibly unlikely for the mean of a sample of 10 numbers or 30 numbers to end up being 99. Okay? And the same can be said about the flip side. For the mean of 30 numbers to be like 5, all the numbers have to be incredibly small. Okay? All the numbers here are equally likely to be selected, so if I select a small number, I might pick another small number, I might pick another big number or something, but if I pick 30 numbers, okay, they're all probably going to average out to be something close to the middle-ish, and that's what we're seeing here. And when we see this, we are essentially getting, or not essentially, we do get the normal distribution here. Okay. And so here, this is a population that was that had a uniform distribution. Okay. And so here's the really nifty part in my, yes.
So wait, you said you could put the numbers back in, so does that mean you're collecting your sample size and then once everything's collected, then you put them back in, or are you selecting one, calculating it, and putting it back in so you can pick it again for the sample?
Yeah, I was sampling with replacement, picking one and throwing it back in.
So you could pick it twice, essentially?
Essentially, yes. And that only makes a difference when your population is small. So here I had only 100 numbers to deal with. So if I'm taking samples of size 30, and I'm not doing it with replacement, what ends up happening is that what I see in my what ends up happening is then I get even more likely to get a sample that is closer to the middle, because, let's say, I pick a bunch of numbers, like I pick the high numbers in the beginning of the sample, then that means by chance, let's say I pick 100, 99, 98, okay, the first three numbers. Then if I'm going to pick 30 numbers total, it's impossible for me to get an average of 99, because I have to pick 30 numbers and these numbers are no longer available, right? So if you do it without replacement on a fairly small population, then it even drives it even further into having a smaller spread. Okay. Was that a question? Just stretching. Okay. Okay, and so we can take the population and it can be even a crazy distribution. So let me do sequence 1 through 15, or actually I want to do repeat 1 through 50, and each will be 50 through 1. Okay. Oops. Is this not? This is not working. Sorry. Okay, this is what I wanted. Sorry. Okay, so here's my population, okay? So I've got this crazy looking V thing where the numbers 0 and the numbers 100 are much more likely, and the numbers, in the middle are much less likely, okay? We can ask, what is the mean of this population? The mean is 50.5 and the standard deviation is 35.24, okay? And we can do the same thing, and I hope this still works. We're going to take samples of size 30, and we're going to ask, what does this look like? So our population looks crazy, like this. We got this bimodal population. What do you think our sampling distribution is going to look like? Repeatedly taking samples of size 30 out of our population and looking at the sample means. Okay, so my population is this crazy bimodal distribution where the numbers 0 or 1 and 100 are much more likely, and the numbers in the middle of the distribution are much less likely. I'm going to take random samples of 30 out of here with replacement, and I'm going to graph all of the sample means that I do. what will this look like? Yeah, let's take a look. Okay, so I've run the simulation. We're gonna create a histogram, and it ends up looking normal still. Okay, and again, and it's just because when I'm taking a bunch of samples or taking a bunch of observations, even if I'm more likely to get a big one or a small one, they end up kind of canceling each other out, and we end up getting centered around the overall mean, looking like a normal distribution. Okay? Essentially, so this is why the normal approximation to the binomial works. Okay? Because the binomial distribution, you're essentially sampling from what? 0 or 1. Okay? You're essentially sampling 0 or 1. Like if I say I'm going to flip a coin 100 times, how many times does it land heads? Okay? Every time you flip the coin, either it lands heads or it doesn't land heads. So you either add 1 to your total number of heads observed, or you add 0 to the total number of heads observed. Okay? So you're essentially sampling from 0 or 1, and if we if we run this simulation again, it's still, we end up getting a normal distribution. Now it's not, it looks a little bit funny here, and that's because when you do 30 flips, you're either going to get 29 heads or 30 heads or 31 heads or something like that, or not, 15 heads or 16 heads or something like that. And so we lose some of the smoothness. Okay, there's this is why we have the continuity correction, but so we lose some of the smoothness, but overall even the 1s and the 0s are equally likely to be selected, and so they kind of end up canceling out, and we end up getting something that looks like the normal distribution. Okay? So all of this to say, the central limit theorem says when we're looking at the sampling distribution of the sample mean, once again, the resulting sampling distribution follows the normal distribution. Okay? There's another property that the central limit theorem states, and that is that the larger your sample, what do you think is going to happen to the spread of the sampling distribution if you take an even bigger sample?
It's pretty small.
The spread gets smaller of the sampling distribution because, you know, if you take 100 people, it becomes even more unlikely to have the average IQ being like 110 or something like that. So with 30 people, it was unlikely for the average IQ to be 110, but with 100 people, and you take the average IQ, it becomes even more unlikely to get the average being 110 or something a distance away from the mean. Okay, so all of that, I hope these demos in R are okay, but all of this to say, what does the sampling distribution of the sample mean look like? Okay, and this is where we learn the central limit theorem. Okay, or the CLT. CLT states that the sampling distribution of the mean will follow a normal distribution. Okay. The mean will be I should say the mean of the sampling distribution will be equal to the mean of the population. Okay, so whatever the mean of the population is, that's going to be the mean of your sampling distribution. The standard deviation of the sampling distribution will be equal to sigma divided by the square root of n. So this is where we see the size of the sample playing into the spread. It's in the denominator, so larger samples mean smaller spread or smaller standard deviation. Okay. But I have to say star if certain conditions are met. Okay, so the central limit theorem says the sampling distribution, of the sample mean will follow a normal distribution, and all normal distributions need a mean and standard deviation, and the mean is the same as the mean of the population, and the standard deviation is sigma, the standard deviation of the population, divided by the size of the sample. Square root of sample size. Is that okay? Okay. So let's try an application of this. Okay. So we will say IQ scores come from a normal distribution, mean 100, 16. We take a random sample of, we'll say, 4 people. Okay, and I'm going to ask, what is the probability that the mean IQ of these 4 people is over 110? And I'll also ask, how does this compare to the probability of a random individual having an IQ over 110. Okay, so I'll give you guys a couple minutes to solve this problem. Okay, well, put the answers up already. I think this is what we should get. Okay, so let's look at the probability that the mean IQ of these 4 people is over 110. Okay, so from the central limit theorem, we know that y bar is going to come from a normal distribution. What is the mean of y bar's distribution? It's the same as the population mean, 100. And the standard deviation of y bar's distribution is going to be 16 over the square root of 4. So we'll get a standard deviation of 8. I hope that's okay. All right, and then so now we're going to calculate a z-score for 110 minus 100 divided by 8. You get a z-score of 1.25. And now I look 1.25 up in the table, and I find the area to the left to be 0.8944. And I want the probability of 110 or more, or is over 110. So I do 1 minus 0.8944, and that gives me 0.1056. Is that okay? All right. And then over here, we're just a random individual, so random y is going to come from normal 100, standard deviation 16, so my z-score is 110 minus 100 over 16. So I do 10 over 16 and I get 0.625. So I have to pick a number, so I'm going to just round off to 0.63. I look that up. And I think if I look up 0.63, I get this number. Let me just double check here. I get 0.7357 or 0.7324. 0.7357. Oh, I guess I had picked 0.62. Okay, well. Okay, and let's see, do 1 minus 0.7357, and then you get 0.2643. Okay. Or halfway in between 0.2643 and 0.2676. It doesn't matter. So we see that the probability that a random sample of 4 people having an average IQ over 110 is much smaller than the probability that a random individual has an IQ over 110. All right, is that okay? So the application of the central limit theorem. So, you know, if you see a normal model problem or, you know, a sampling distribution problem, make sure you know when you're dealing with an individual, where you just use the standard deviation provided to you, and when you're dealing with a sample, where you have to take the standard deviation, divide by the square root of your sample size. Okay? All right, so let's talk about the conditions that are necessary to use this central limit theorem. Okay, so there's a little star, and I'll say the central limit theorem only works under certain conditions. Conditions or assumptions. Okay, the biggest one that, you know, in textbooks it's easy to take care of, but if you ever wanted to apply statistics to real life, this is probably the biggest assumption or condition that's hard to satisfy, and that is the sample is chosen randomly from the population. Okay, chosen randomly from the population, or I should say, is a simple random sample. So again, in real life, it's quite difficult to pull off the simple random sample, but our the mathematics going behind the central limit theorem. So I kind of just said this is the central limit theorem and this works, without deriving how it works. I just showed you some histograms in R and said it works. The central limit theorem is true. And we're so we're avoiding the mathematical derivation of the central limit theorem, which I think is okay because it involves calculus and is rather intensive. But if you know that the central limit theorem works for the sampling distribution, I think that's okay. All right, and so but the mathematics assumes a simple random sample. Here are a few other things, okay? The sample we select is either done with replacement or is less than 10% of the population. Okay, and so, we generally only have to worry about this if we're dealing with a very small population. Usually, the population that we're interested in is very big, so we don't ever have to worry about sampling more than 10% of the population. But the worry here is that if you were to sample too much of the population, your sample would affect what remains in the population. So just like I said, if we were taking samples of 30 out of the population of 100 without replacement, then what we draw in the sample affects what's left in the population to be selected from. What we say is that if your sample is less than 10% of the population, the impact that it has is negligible, so we don't have to worry about it. Okay, and then the last one, this is the one that we generally have to check the most often for. Okay, so in terms of real life, the simple random one is probably the hardest to pull off, but this is also one that we also have to check for. Is that the sample we select is quote-unquote large enough. And this is purposely vague because it is kind of vague, okay? So what does large enough mean? It means if the population is normal, if somehow we know the population is normal, then any size sample is large enough. Okay, any sample we draw will be large enough. However, if the population is not normal, so for example, it's skewed or something like that, okay, then we need a bigger sample. Rule of thumb is n greater than or equal to 25, or some textbooks will say 30, is generally large enough for most situations. Okay? But in very skewed situations, okay? But in very skewed distributions, even larger samples will be required. And there's no magic number that says this guarantees a normal distribution, okay? It's just, for most day-to-day situations, samples of 25 or more will be big enough. Other textbooks might say 30. But for skewed distributions, you'll need even bigger ones. And sometimes you might want to put some kind of transform. You might want to take the log of all the numbers you have, or take the square root of all the numbers you have. It all depends. But the rule of thumb is most situations in life, 25 is big enough. But if you get something really skewed, like income distributions, then 25 will not be big enough. And probably the only way to handle income distribution will be to take the log of those values. But there you have it. So these are the conditions that need to be true to use the central limit theorem. Are there any questions? No? Okay, why don't we take a short break here, and we'll come back and we'll start talking about confidence intervals.